And welcome back to another exciting session of Math A&I HL. We are now on section 9.3, solving systems of equations using matrices. So even though you don't technically need matrices to solve such systems, in fact, in your lower level high school classes, you've already seen some systems of equations solved by the elimination method, by the substitution method, by the inferior graphing method. Matrices gives us another method, which, while perhaps not the most efficient for 2x2 matrices, does become the best method as the number of variables increases. Plus, we get to finally see a use for matrices besides a way of organizing the data in a organized fashion. We actually see practical applications of matrices. Now we're going to start with the following situation. Suppose I gave you the following system of equations. 10x minus 5y is equal to 35, and negative 3x plus 7y is equal to 23. Now, we're not going to solve this system, not yet at least, but let's talk about it for a second. What we see here is as follows. We have a system of two equations with two unknowns. And that's what we're going to focus on for the time being. A certain number of equations with an equal number of unknowns. Two equations with two unknowns, three equations with three unknowns, four with four, and so on. How do we solve this? We're looking for a pair of numbers, one for x, one for y, that makes both of these equations true at the same time. And again, as mentioned, substitution, elimination, graphing, we have techniques for doing so. But we want to learn a new technique, and that technique is using matrices. And the first thing we have to realize is that this pair of equations is equivalent mathematically to the following matrix equation. And we'll see why or how. So the numbers in the 2x2 matrix, because two equations, two unknowns, are the 10 in front of the 10x, the negative 5 in front of the negative 5y, the negative 3 in front of the negative 3x, and the 7 in the 7y. The first 2x1 matrix here are just your two variables x and y, and the equal matrix on the other side are the two numbers 35 and 23. Why are these equivalent? Well, let's think about it. If you take these two matrices here and you multiply them out using our rules for multiplication, you get a 2x2 times a 2x1. Those two numbers are equal, so I'm allowed to multiply, giving me a 2x1 matrix, which is, of course, what I end with. And how do I do that? Well, you take the first number in the first row and the first number or value in the second matrix's column, and you multiply 10 times x, negative 5 times y, so 10x minus 5y, and that equals 35. Similarly, negative 3 times x plus 7y equals 23. So these matrices, this matrix equation is equivalent to the original problem. In the case of a 3x3, it's no different. If I do 4s minus 3t minus 2z equal to 0, one equation, three unknowns, 2f plus 2t plus 3z equals negative 6, another equation with the same three unknowns, 6s plus t minus z equals 2, a third equation, the same three unknowns. These three are equivalent to, and let's see if we can figure out what this is. It's going to be a 3x3 matrix. What are the numbers? 4, negative 3, negative 2, 2, 2, 3, 6, 1, and -1. My 3x1 matrix are my unknowns, in this case, S, T, and Z. And on the other side, what's it equal to? My three values, 0, -6, and 2. So all we've done so far is we have written these systems of equations using matrices, but we haven't actually seen how to solve them with matrices. So to do that, we're going to consider the following. When you rewrite the system in this way, we're going to call this 3x3 or 2x2 matrix, the matrix of values A. The unknown matrix, the one that we're looking for, X, and the matrix of values we're going to call B. So we have the equation AX is equal to B. And what's the goal? What are we looking to do? Goal, solve for X. Now, if these were numbers, I would just divide by A, but we haven't defined division of matrices, nor are we going to define division of matrices. That's not something that we do. So how in the world do I get rid of the A to get X by itself? And the answer is we're going to multiply on the left of both sides by the inverse of A. What exactly is the inverse of A? Well, as we mentioned, I think in the last section, I'm just confirming that we did not talk about inverses yet. So let's do so now. What is the inverse of a matrix? The inverse of a matrix is that matrix which, when you multiply the original by its inverse, gives you the identity. This is similar to saying 3 times the inverse of 3 is equal to the multiplicative identity. 3 times 3 inverse is the multiplicative identity, is the number that when you multiply it by anything gives you that same thing back, namely the value 1. So if I can find a matrix such that when I multiply, such that it has an inverse, well, then I can use the associative rule that says A inverse AX is equal to A inverse B. Anything times its inverse is the multiplicative identity. So AX is equal to A inverse B. And what's the property of the multiplicative identity? Anything times the multiplicative identity is itself. And therefore, X is equal to A inverse B. So if I have the original matrix equation AX equals B, all I need to do is find the inverse of A, multiply by B, and bam, I have my X. Easier said than done. How do we find the inverse of a matrix? So that's the question. Given a n by n matrix, it's got to be square, an n by n matrix A, how do we find A inverse? And even more fundamental, the question is, does A inverse always exist? And the answer to the second question is no. And you can think about it in terms of numbers. 3 times 3 inverse is equal to 1, sure. But what is the inverse of 0? 0 times what is equal to 1? Well, this doesn't even make any sense. 0 has no inverse. So just like not every number has an inverse, in fact, most do, just one doesn't. Not every matrix has an inverse. So how do we know if it has an inverse? And if it does have an inverse, how do we find it? So answer. So you're in luck. For 3 by 3 matrices and above, now what I mean by above, 4 by 4, 5 by 5, and so on, just use your calculator. The IB does not require you to learn some of the more advanced techniques for finding an inverse, so your calculator can do all the work for you. But in the 2 by 2 case, you do need to know. And when I say you do need to know, just be aware The formula booklet gives it for you. However, the solution or the answer is in your formula book. So what is the answer? If A is the 2 by 2 matrix A, B, C, D, then A inverse is the following. So what you do is you take those two numbers in the top left and the bottom right, we call it the main diagonal, and you flip them. So D goes up left and A goes bottom right. You take those two numbers in the minor diagonal and you make them negatives of whatever they are. So if they're positive, they become negative. If they're negative, they become positive. And then you divide by AD minus BC, the number AD minus BC, which is the product of the main diagonal minus the product of the minor diagonal. And what you get at the end is A inverse, is the inverse of the matrix. AD minus BC is so important that we give it a name. It is called the determinant of matrix A, often written as the determinant of A, or just A in, I guess we would call them absolute value signs, but they're not. It's a determinant sign. What's the determinant of a 3 by 3 matrix, a 4 by 4 matrix, and so on? Don't worry, you don't have to know. It is defined, it is important, but you don't need to know it. Notice, by the way, that this also gives us the answer for when A inverse is not defined. Because if we're dividing by a number, we know that there's one number that we can never divide by. What's that one number that we can never divide by? 0. So if the determinant of A is equal to 0, then A inverse does not exist. So given that those pieces of information, let's go ahead and do some examples. So first, A equals 1, -2, 3, -4. What is A inverse? Well, just follow the rules. The 1 and the -4 switch places. So -4 goes top left, 1 goes bottom right. The two minor diagonal elements change signs. So -2 becomes +2 and 3 becomes -3. And then we divide by 1 times -4, which is -4, minus -2 times 3, which is -6. So again, just simplifying, we have -4, 2, -3, 1, divided by -4 minus -6, -4 plus 6, that's 2. And how do we divide? By a number. It's the same thing as multiplying by 1/2, dividing by 2 and multiplying by 1/2, which means you just divide each one. -4 divided by 2, 2 divided by 2, -3 divided by 2, 1 divided by 2. And we have A inverse. Not solving matrix equations yet, just getting us a little familiarity with finding inverses. So let's do another example. Suppose the matrix P is a 3 by 3 matrix of 4, -3, -2, 2, 2, 3, 6, 1, -1. And the question then becomes, what is P inverse? Well, as I mentioned before, you do not need to do this by hand, but you do need to know how to do it on the calculator because the IB may very well ask you to do so. So here's what you do. You start out by hitting second matrix. Second is the first column, second row. It's the blue button turning you into blue mode. And a few buttons beneath that, 3 buttons beneath that, you'll see the word matrix. So second matrix. That takes you to a screen that looks something like this. Now I happen to have lots of matrices already in there. Yours might be blank. But what you see is names, math, edit. So go right to edit. And then whichever matrix you want to pick, I'll use A. You want to hit enter by it. You want to scroll down till you have the matrix that you want to use and you hit enter. The first thing it asks is for you to put in the size. We're going to do a 3 by 3. And then we put in all the actual values. So I have a 3 by 3 matrix in there, and I've already put in 4, -3, -2, 2, 2, 3, 6, 1, -1. So do that. You can always pause while you're doing it so I don't go past you. Once it's done, hit second, quit. Quit is just to the right of second. Then go back to second matrix, and this time go to math, go to the right. Actually, I lied. Don't go to the right. Just stay with the original, with the first one, and just straight up hit enter. Now, of course, if you're going to use B or C or D or one of the other ones, you might want to scroll down before you hit enter. But here I just have enter, and A, matrix A goes to the stack, goes to the main screen. And then I hit inverse, X inverse button, which is the same as the matrix button, but not in the second mode. So I have A inverse, and I hit enter, and I get this answer with lots and lots of decimals. I don't like decimals, so I'm going to hit math, enter, enter, and it goes to fractions. So I get 1/12, 1/12, 1/12, and -1/3, -2/15, 4/15, 1/6, 11/30, and -7/30. So 1/12, 1/12, 1/12, -1/3, -2/15, 4/15, 1/6, 11/30, and -7/30. We have P inverse. Are we sure it's P inverse? Well, we can always trust the calculator, or we can follow the directions, which says verify that if you multiply P times P inverse in either order, by the way, it has to be in both P times P inverse or P inverse times 3, that we do in fact get the identity. This particular example is the 3/3 identity. So we're not going to do all the calculations, but you certainly can. But if we take P and multiply it on the right by P inverse, we have a 3/3 times a 3/3. We know that's defined, giving us a 3/3, which is wonderful. So that means we have 9 calculations to make. And the first entry is in the first row, first column. So first row, first column, 4 times 1/12, that's 4/12 or 1/3, minus 3 times -1/3, so plus 1. And then minus 2 times 1/6, minus 2/6, minus 1/3 is in fact equal to 1. And if you do the rest, you will hopefully see that you do in fact get the identity. And similarly for P inverse P, you should also get the identity. So now let's go ahead and go one step further and show how we can use this fact of finding inverses to actually solve a system of equations. And we're going to start with those equations that we had in the beginning. So I'm going to copy this, 10x, and duplicate it. 10x minus 5y equals 35, and -3x plus 7y equals 23. And we already know that this is equivalent to 10, -5, -3, 7, x, y equals to 35, 23. And therefore, xy is equal to the inverse of 10, -5, -3, 7 times 35, 23. X equals A inverse B. That's this one right here. X equals A inverse B. That's the big one. Just take the inverse of your coefficient matrix times B, and you should have the answer. Well, let's do that. What's the inverse of this 2x2 matrix? Well, the 10 and the 7 switch places. The -5 and the -3 switch signs. Divided by 70 minus 15 times 35, 23. So let's see what we get here. It's a 2x2 times a 2x1. So we know it's going to be a 2x1 7 times 35, what is that? 7 times 30, 210, 245, plus 5 times 23, that's what, 115. And then we have 3 times 35 is 105, plus 10 times 23 is 230, still divided by 55. 245 plus 115 is 360. And then 105 plus 230 is 335 over 55. 360 divided by 55 is some annoying number. My calculator tells me it's 72 over 11. And 335 divided by 55 is another annoying number, which my calculator tells me is 67 over 11. And checking the book, those are the correct answers. So xy equals 72 over 11, 67 over 11. We have solved the system for x and for y. How lovely is that? Let's do another example. This time, suppose we have the other starting problem, which was 4s minus 3t minus 2z equals 0. 2s plus 2t plus 3z equals -6. And 6s plus t minus z is equal to 2. So here we have same thing we started with earlier. This is a 3 by 3. How do I solve this? Well, the same way. S, T, Z, the thing that I'm looking for, is the inverse of 4, -3, -2, 2, 2, 3, 6, 1, -1 times 0, -6, 2. Well, how do I find the inverse of this matrix? The 3 by 3. So this is a calculator problem, second matrix. Edit. I do A again. It's a 3 by 3. Oh, I already have this one. I already have the answer. Do I? 4, -3, -2. Look at that. This is lovely. We've already solved this one in the previous problem. Didn't even realize it. Those sly dogs. So we get the answer that we already had. I'll quit out, so I'll just do it again. Math, the A inverse, and we get fractions. So we get 1/12, 1/12, 1/12, -1/3, -2/15, 4/15, 1 over 6, 11 over 30, -7 over 30 times 0, -6, 2. Do I really want to multiply this out? No, I don't. And I already know how my calculator can do multiplication. So all I have to do is throw in the 0, -6, 2. So second matrix, edit. B will be a 3 by 1 matrix. 0, -6, 2. Quit out. And let's multiply A times B. And this gives me -1/3, 4/3, and -8/3 as my S, my T, and my Z. And that's exactly what the calculator, what the book gives me. So I'm happy. Everything's working out great. We now know how to solve a system of equations using matrices. Is it always the most efficient way? No, it's not always the most efficient way, but it's a way. And the more ways we have at our disposal, the more options we have, it can't get any worse. Now, at the end of section 9.3, before the exercises, 9D is a section on cryptography. So what is cryptography? So cryptography is code making and code breaking. I remember as a kid, a friend of mine and I used to pass notes to each other in class. And what we would do is we would pass English sentences, but use a different language. We both spoke Hebrew, so we would, like if I want to write the word, candy, okay, which in English is spelled C-A-N-D-Y, I would, Dawid. It's been so long since I did this. Dawid, I think it's, wow, incredible. I don't remember. Something like this. I don't even remember how to do a Dawid. But, well, that's sad. Anyways, so cryptography has a long and storied tradition of making codes, breaking codes. This is the cornerstone of internet security, although they use different cryptography than we're going to do here today. They use a fascinating type based upon RSA cryptography. Rivers, Shamir, and Edelman, who came up with it, I think, in the 70s, maybe even the 80s. There's some fascinating stuff, but we're going to use some basic cryptography. And what we do is as follows. We first assign symbols and letters, we give them numbers. So on page 388 of the textbook, we have a list. A is 1, B is 2, all the way down to Z being 26, capital A 27, all the way down to capital Z being 52, and then there's the exclamation point is 53, and lots of other symbols, all the way to the number 9 being 76, and a space being 77. So even though the number 9 and 8 and 7 are there on the left, we're going to imagine them as just being symbols, and the numbers on the right are the numbers 1 through 77. And we want to pass a message. We want to send a code. And in this particular example, the code that we're going to use is, so we want to encode the following. So capital C-H-A-R, capital L-I-E, 578, capital S-A-M, star, exclamation point. And that is that's the thing that we want to encode. I want to send this. Someone says, hey, what's the password to your bank account? And they go, well, I'm not just going to send the password to my bank account because then anyone can steal it. I'm going to encode the password using numbers and send numbers instead. Now, if I just send the numbers, it's not hard. If I send the number 1, you're like, oh, 1, well, that's A, and 2, oh, that's B. So the first step is to translate the code to numbers. So for example, capital C is 29, lowercase h is 8, lowercase a is 1, and this is all on the on page 388. I'm just copying from the book, which was very nice to write it all out. 74, 75, 45, 1 again, 13, 60, and 53. Let's make sure we have the right number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. I have 15 numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay, 15. So we've encoded those 15 numbers. The question is, I don't want to send these 15 numbers. I want to encode these 15 numbers and send different numbers. How do I do that? Well, the first thing I have to do is I have to decide on my encoding and decoding matrices what size I want to use. The book in particular uses a 3x3. You don't have to, but the book uses a 3x3 coding matrix. And this matrix that they use, 7, 2, 1, 0, 3, -1, -3, 4, 2, is an arbitrary 3x3 matrix with one condition. that one condition is its determinant cannot be 0. So one condition, let's make a big dot here. One condition on coding matrix is its determinant is not 0. Let's just check. How do I find the determinant of the matrix? No problem. Second matrix on my calculator, especially it's a 3 by 3. Edit. I'm going to do A 3 by 3, 7, 2, 1, 0, 3, negative 1, negative 3, 4, 2. Second quit. Second matrix. With the right to math. And the very first one on the list is the determinant. Det. The very first one on the list. Second matrix, A, determinant of A, and it gives me, right, in our case, the determinant of C is equal to 85. So we're good to go, 85. And what we're going to do now, okay, so step 1 is, let's actually do this. Pick a square coding matrix of your choice. Okay, you can say, hey, how can the book pick this one? The book picked this one because it had to pick something, so I picked this one. Okay, just pick a coding matrix, got to be square of your choice. Its determinant cannot be 0. In this case, the determinant of C is 85. It's not equal to 0. Next, take your numbers and make a column matrices of the appropriate size. So 29, 8, 1. Remember, it's a 3 by 3 matrix, so we're making column vectors of size 3. 29, 8, 1, 18, 38, 9. Next is 5, 72, 74. Next is 75, 45, 1. And then 13, 60, 53. Now notice that there's 15 numbers, and using the 3 by 3 matrix worked out perfectly. We had exactly the right number. We had 5 columns. What if I had 16 digits? Well, you can always use a 4 by 4, and then you'd have 4 columns. Or you can still use 3 by 3, and any of the leftovers, you can just use spaces. So you can always add up. Remember, if you go back here, right, 77 spaces, you can always, of course, just have empty spaces at the end. But you have to have each of the column matrices must be of the appropriate size. So create, this is step 2, or create column vectors or column matrices. We don't know what a vector is yet, depending on what chapters you've covered, but create column matrices of the appropriate size containing the message to be encoded. Okay, so that's the first 2. And then 3, actually encode it. Your encoding matrix E is equal to your coding matrix times the message matrix. In our case, the encoding matrix is 7, 2, 1, 0, 3, negative 1, negative 3, 4, 2. And our message matrix is a single matrix containing all of these numbers. I don't look at it as 5 separate column matrices, but I create one big 3 by 5 matrix. 3 by 3 times 3 by 5 gives me a 3 by 5, which is great, because if I start with 15 numbers to be encoded, I want to end with 15 numbers to be encoded. Now, second matrix, I already have my A as my 3 by 3. In this case, I'm going to go to edit, and I'm going to make my B a 3 by 5, 29, 18, 5, 75, 13, 8, 38, 72, 45, 60, 1, 9, 74, 1, and 53. Second quit, second matrix, A times second matrix, B. This gives me the following: 220, 211, 253, 616, 264, 23, 105, 142, 134, 127, negative 53, 116, 421, negative 43, and 307. So I send my encoding matrix, and you intercept it. And you look at this, and you see these new 15 numbers. Well, those numbers may or may not appear on the original list, but they certainly don't correspond to the letters that they started with. I mean, some of them are negative in the 200s. We only have up to 77. So you're looking at these numbers, and you cannot decrypt them because you do not know where they started from. The only one who knows where they started from is whoever has the coding matrix C. So you can't do much with them. Now, when I send this message to my friend gets this message. Now my friend must decode it, right? So step 3, of course, is encode the message using the coding matrix C. So what is step 4? Decode the matrix. Decode, I guess, the matrix. E. How do I decode the matrix E? Somehow I have to get rid. Remember what E was? E was Cm. So I have this equation E equals Cm, and I want to solve for M. What was my original message? Well, how do I get M by itself? I got to get rid of C. How do I get rid of C? I can't divide by C, but what can I do? I can multiply by C on the left. If I multiply by C on the left and use the associative property of matrices, I see that the original matrix is nothing more than C inverse times E. What is C inverse? Well, go back to my calculator. My first matrix inverse using fractions. So C inverse, you should do this yourself. I get 2 over 17, 0, negative 1 over 17, 3 over 85, 1 over 5, 7 over 85, 9 over 85, negative 2 over 5, and 21 over 85. And if I take that and multiply it by my encoding matrix, answer times this one. Well, my calculator tells me a syntax error. I haven't been able to figure out my calculator how to do this. But if I do C inverse times the encoded matrix, I do get back the original. So I'm going to take this and duplicate it. And then I'm going to take this and duplicate it without the equal sign. So if I take C inverse times E, I get my original matrix M. Yay. Then I get to read it, and I get my original message back. Encoding and decoding matrices. Okay, so let's now move on to exercise 9D. As always, when it comes to the exercises, you should always be trying every one of these yourself before seeing the answer. Question 1. Determine the multiplicative of each matrix using the A inverse equals 1 over the determinant of A, switch those two, negate those two, and then verify your answer by showing that A inverse is equal to I. So the first one, A. We have the matrix A is equal to 2, negative 4, 3, -5. So first, let's find A inverse. How do I do that? Again, you should be pausing and doing it yourself. The -5 and the 2 switch places. The 4 and the -3 are the opposite signs. And then we have -10 minus -12. So that means -10 plus 12 is 2. So -5 over 2, 4 over 2, -3 over 2, 2 over 2. So there's A inverse. Now we have to verify that A inverse is actually the 2 by 2 identity. So 2, -4, 3, -5, and -5 over 2, 2, -3 over 2, 1. 2 by 2 by 2 by 2 does in fact give me a 2 by 2. 2 times -5 over 2 is -5, plus 6 is 1. 4 minus 4 is 0. -15 over 2 plus 15 over 2 is 0. 6 minus 5 is 1. That direction works. Then we do A inverse A, which is the reverse direction. It's got to be true for both. -5 over 2, 2, -3 over 2, and 1. With 2, -4, 3, -5. -5 plus 6 is 1. 10 minus 10 is 0. -3 plus 3 is 0. 6 minus 5 is 1. Hey, this is a 2 by 2 identity. This is a 2 by 2 identity. A works. B. Let's change colors here. B. So in this case, A is equal to -2, -3, -1, 0. So what is A inverse? Well, those two flip, those two change sign, and we divide by 0 minus -3. So what do we get? 0, 1, 1/3, and -2/3. Well, what is A inverse? -2, -3, -1, 0 times 0, 1, 1/3, -2/3. 0. -2, -3, -1, 0. Those two flip, those change sign. Aha. This should be 0 minus 3. Whoops. So -1, -1/3, +2/3. See, when you know what you're doing strategy-wise, but the number is not working out, check your work. Did you make a silly mistake? We're all susceptible to that. So just check your work. In this case, now I get 0 plus 1. Then I get 2 minus 2. Then I get 0 plus 0. And then I get 1 plus 0. So that worked. A inverse A is the other direction. 0, -1, -1/3, 2/3 times -2, -3, -1, 0. 0 plus 1, 0 and 0. 2/3 minus 2/3, and 1 plus 0. So that one worked as well. This is equal to the 2 by 2. This is equal to the 2 by 2 identity matrices. Another color, let's move on to green, C. In this case, A is the annoying fractional matrix, 3/4, 1/2, 1/2, 3/4. So what is A inverse? You flip those. Oh, well, that's convenient. They're the same. You negate those. And then you divide by 9/16 minus 1/4. That's 9/16 minus 4/16. That is 5/16. So I'm just going to cross it out and write 5/16 equals 3/4 divided by 5/16 is what, 12/5? Negative 8 over 5, negative 8 over 5, and 12 over 5. Let's see if that's right. What is A inverse if I'm right? Well, we have 3/4, we have 1/2, we have 1/2, we have 3/4. We have 12/5, negative 8/5, negative 8/5, 12/5. Whew, so 3/4 times 12/5. That's 9/5. It's not working. 9/5 minus 8/10. 18/10. Oh, 18/10. Yeah, 1/10. That's 1. Yes. Negative 24 over 20 plus 12. Yeah, that works. And then we have 12 over 10. That's 6 over 5 minus 24 over 20 minus 12 over. Yeah, that works too. And then we have negative 4/5 plus 9/5 by A. Look at that. It worked. I love it. And then A inverse A is 12 over 5, negative 8 over 5, negative 8 over 5, 12 over 5. And then 3/4, 1/2, 1/2, 3/4. So what do we get? We get 9/5 minus 4/5. 5/5 is 1. Then we get 6/5 minus 6/5 minus 6/5 is 0. Negative 6/5 plus 6/5 is 0. And then negative 4/5 plus 9/5, 5/5 is 1. Hey, love it. Notice that I didn't just assume it was correct, but I actually went ahead and did the math. And then D, we have A is equal to 0.25, 0.8, 0.75, 0.2. I'm going to first rewrite this as 1/4, 4/5, 3/4, and 1/5. Decimals are double, go to fractions instead. So what is A inverse? Well, those switch, 1/5 and 1/4. Those change sign. And then we divide by 1 over 20 minus 12 over 20 minus 11 over negative 11 over 20. So what do I get? I get negative 11, negative 44, negative 16. Can that be right? That can't be right. 20 over negative 44 is good. 20 over negative 16. Don't forget times 11. So trying to do this in my head, but calculators work just fine. 4/5 divided by 11 over 20 as a decimal is 16 over 11. Let me try that one more time. Well, first negative over negative, that goes away. So 0.8 divided by 11 over 20. Well, I guess it is 16 over 11. So let me double check my other one. 1/5 divided by 11 over 20. Well, that's just 4 over 11. That was not even close, negative 44. Negative 4 over 11. 3/4 divided by 11 over 20 is 15 over 11, and 1/4 divided by 11 over 20 is 5/11. So let's do A times A inverse. 1/4, 4/5, 3/4, 1/5 times -4/11, 16/11, 15/11, 5/11. That's -1/11 plus 12/11. 11/11 is 1. 4/11. Uh-oh. Well, that can't. Oh, that should be. That should be -5/11 down there, not positive. Okay, much better. So 4/11 minus 4/11 is 0. -3/11 plus 3/11 is 0. And 12/11 minus 1, 11/11 is 1. Beautiful. And then A inverse A is -4/11, 16/11, 15/11, -5/11 times 1/4, 4/5, 3/4, and 1/5. So -1/11 plus 12/11, 11/11 is 1. -16/55 plus 16/55 is 0. 15/44 minus 15/44 is 0. And 12/11 minus 1/11, 1/11 is 11/11 is 1. Fantastic. So that is question number 1. Whew, that took a while. Okay, question number 2. Uh-oh. Question number 2. Oh, what happened here? I went away. So we already did the math. We don't got to do it again. Okay, so question number 2. That's not straight. Okay. It says determine the multiplicative inverse of each matrix using technology expressing the elements at exact values and verify your answer by showing that A inverse equals I. So this one's going to be a little faster, even though we have 3x3 matrices, because we're going to use our calculator to do it all. First one is 2, -1, 4, 1, 2, 0, -1, 1, 2. So second matrix, edit A, 3x3, 2, -1, 4, 1, 2, 0, -1, 1, 2, quit. And second matrix, A inverse, math, enter, enter. So A inverse is equal to 2/11, 3/11, -4/11, -1/11, 4/11, 2/11, 3/22, -1/22, and 5/22. So I'm going to assume, without actually doing it, just for the interest of time, but you should do it, that A inverse, or A inverse A, are both equal, in this case, to the 3x3 identity matrix. Part B, A is equal to 1.2, -2.5, 3.8, -1, 4, 1.5, -0.75, and 1. How do I find A inverse? No problem. Second matrix, edit A, 3x3 again, 1.2, -2.5, 3.8, -1, 4, 1.5, 0.75, and 1. Second quit, second matrix, A inverse, math, enter, enter. So what do we get? We get 8/23, -19/46, 14 over 23, negative 52 over 115, 33 over 115, 24 over 115, negative 21 over 115. That was like a 4. Let's fix that. Negative 21 over 115, 93 over 230, and negative 8 over 115. And like before, without actually doing it, I'm going to assume, you shouldn't assume, but I'll assume that A inverse equals A inverse times A is equal to the identity matrix. And then we have C. A is 2/3, negative 3/4, 1/2, 1, 1/3, negative 1, 5/2, 0, 1. What is A inverse? No problem. Second matrix. Edit A, 3 by 3, 2/3. I can actually do 2 over 3 on your matrix. Negative 3 divided by 4, 1 divided by 2, 1, 1 divided by 3, negative 1, 5 divided by 2, 0, 1, quit matrix. Inverse, math, decimal, decimal. What do I get for A inverse here? I get 24 over 175, 54 over 175, 6 over 25, negative 36 over 25, negative 6 over 25, 12 over 25, negative 12 over 35, negative 27 over 35, and 2 over 5. And again, we'll just assume, I'll assume, you prove it, that A inverse equals A inverse times A is equal to that matrix. Okay, moving on. Question number 3. It says write each system in the form of AX equals B and then solve using X equals A inverse B. So the first system here is X plus Y plus 3Z is equal to 30. 3X plus 2Y minus Z is equal to 20. And then 2X plus Y plus Z is equal to 10. This is equivalent to 1, 3, 3, 2, negative 1, 2, 1, 1, times the unknown X, Y, and Z is equal to 30, 20, 10. So what is X, Y, Z? X, Y, Z is the inverse of that matrix times 30, 20, 10. What's the inverse? No problem. Second matrix. Edit. We got a 3 by 3, 2, 1, 3, 3, 2, negative 1, 2, 1, 1. Uh-oh. 2, 1, 1. My numbers are correct. Second matrix quit. Second matrix. A inverse, not bad. Negative 1.5, negative 1, 3.5, 2.5, 2, negative 5.5, 0.5, 0, negative 0.5. And I want to multiply this by another matrix. I'll edit the second one, make it 3 by 1, 30, 20, 10, quit out. So we take this matrix here and we multiply it by this matrix, and it gives us negative 30, 60, 10. So this is part A. Let's assume that's correct. Nice, never better get it checked. Negative 30 plus 60, that works. Negative 90 plus 120, man, that works. Okay, beautiful, it works. B, we have the system 5x minus 7y is equal to 12. Negative 2x plus 5y is equal to 20. This is a 2 by 2. So I'm going to do this one by hand. First, we have 5, negative 7, negative 2, 5, times my unknown x and y equals my values 12 and 20. So what is my unknown x and y? It is the inverse of this. Those switch places. Those change signs. Divide by 35 minus 14 times 1220. 35 minus 14 is 21. So I get 5 over 21, 1 over 3, 2 over 21, 5 over 21 times 12 and 20. Oh, why did I do this by hands? Okay, so 60 over 21. You know what? Let's get a common denominator. Let's keep this as 7 over 21. So I have 1260 and 140, so 200 over 21. And the other one is 24 plus 100, 124 over 21. Well, that wasn't half bad, assuming I did it right, which you never really know. Working quickly, trying to get these videos not excessively long. I am working a little quicker than I would do if like my life was on the line. So it's certainly possible that there are some mistakes. If you find them, always let me know. This one, 2a plus b minus c plus 4d is equal to -2. 4 variables. Hopefully we have 4 equations. 5b minus 3c is equal to 4. 4a minus 3b plus d is equal to 1.75. And a plus 2c minus 8d is equal to -0.5. So first we rewrite it, matrices, 2, 1, -1, 4, 0, 5, -3, 0, 4, -3, 0, 1, 1, 0, 2, -8 times my unknowns a, b, c, d equal -2 for 1.75 and -0.5. So what are my unknowns? A, B, C, D. Oh, here we got a 4 by 4. No problem. Edits. Hey, make it a 4 by 4. 2, 1, -1, 4, 0, 5, -3, 0, 4, -3, 0, 1, 1, 0, 2, and -8. Second quit, second matrix, just inverse. Oh, that's ugly, but with fractions, it's not much better. Oh, let's make another one, a 4 by 1 this time. Second matrix, edit, second one, make it a 4 by 1. We got -2, 4, 1.75, -0.5. Yes. So back to the stack. Multiply that times b, and we get -91 over 254, -172 over 127, -456 over 127, -447 over 508. Ugly, ugly numbers. Let's hope they're correct. Okay, now moving on to the good stuff. Question 4 now. It says, for questions 4 through 6, create a system of equations that represents each situation and then solve the system using matrices. Be sure to define all variables. No problem, I can do that. So, 4. In 2016, Sonia invested a total of $175,000. That's a lot of money. In 3 different index funds, Fund 1, Fund 2, and Fund 3. After 1 year, the combined value of all of her investments was $181,615. Okay, so this is a time t equals 0 and the time t equals 1. It's now worth $181,615. How nice. Data collected on each of the investments showed that each investment made average annual gains of 2.5%, 4.8%, and 3.5% respectively during the year. Now, if Sonia invested twice as much money in F2 than in F1, so F2 is twice F1, calculate the amount that she invested in each fund. So there's 3 unknowns, which means if we're going to use this whole matrix approach that we're working with, we need 3 equations. One equation is that the amount invested in the first plus the amount invested in the second plus the amount invested in the third must be 175,000. The second equation is if you take what she invested in the first one and add 2.5% of that, and you take what she invested in the second one and add 4.8% of that, and take what she invested in the third and add 3.5% of that, that adds up to 181 and 615. And then the last one is 2f1 minus f2 is equal to 0. 3 pieces of information, 3 unknowns, 1, 1, 1, 1.025, 1.048, 1.035, 2, -1, 0. My unknowns, f1, f2, f3, equals my 3 coefficients, 175,000, 181, 615, 0. How do I solve? Well, we know how to do this. We take the first matrix, 3 by 3. Oh, that means it's a calculator. So second matrix, edit. First one, 3 by 3. Oh, not 3 by 4, 3 by 3. 1, 1, 1, 1.025, 1.048, 1.035, 2, -1, 0. Matrix. Added another one. My second matrix will be a 3 by 1 matrix of 175,000, 181, 615, and 0. So now we go to A, and we want inverse. Whoops. A inverse. Multiply that by B, and we get 30,625. 61,250, 83,125. And just admit it, that was a lot faster than any other method you're familiar with. I mean, of course, you got to know how to solve these problems. But once you solve these problems, that was pretty fast. Just admit it. Okay. Anywho, question number 5. It says, a manufacturer wishes to produce 4 different products, A, B, C, D. The table below shows the number of minutes required on each of the 4 machines to produce the product. So we have the following table. We have machine 1, machine 2, machine 3. Well, that's not how you do it. 4, machine 4. And we have product A, product B, product C, and product D. 2, 1, 1, 3, 1, 3, 2, 4, 2, 1, 2, 2, 3, 4, 1, 2. Let's again go over the question, make sure we understand. A manufacturer wishes to produce 4 different products, A, B, C, D. The table below shows the number of minutes required on each of the 4 machines to produce each product. So if I want to use machine 1 for product A, it would take 2 minutes, and so on. The maximum amount of time available for each machine 1, 2, 3, and 4 is, so the maximum is 240 minutes. So it must be less than or equal to 240. The second one must be less than or equal to 380 minutes. The third one must be less than or equal to 280 minutes. And the fourth one, we only have 400 minutes. Calculate how many of each product can be manufactured if each machine uses all of its available time. Well, first I can now change those. Those are not less than or equal to anymore. Those are exact. So we're going to use 240 minutes for machine 1, 380 for machine 2, 280 for machine 3, and 400 minutes for machine 4. And we want to calculate how many of each product. So our unknowns are A, B, C, and D. 4 unknowns, which means if I want to use this matrix approach, I need 4 equations. Where are those equations going to come from? Well, let's think about it. If I'm using machine 1. That means that 2 minutes for each A, plus 1 minute for each B, plus 1 minute for each C, plus 3 minutes for each D, must total 240 minutes. And the other ones are, of course, similar. Once you know how to set up the first one, then the other ones kind of are obvious. And how do I do this? Well, this is not a problem. 2, 1, 1, 3, 1, 3, 2, 4, 2, 1, 2, 2, 3, 4, 1, 2 times my unknown A, B, C, and D has to equal 240, 380, 280, and 400. So how do I find my A, B, C, D? No problem. Take out your calculator, matrix, edit, first one, 4 by 4. 2, 1, 1, 3, 1, 3, 2, 4, 2, 1, 2, 2, 3, 4, 1, 2. Second matrix is going to be a 4 by 1 of 240, 380, 280, 400. Quit out. First one, inverse, times second one. Ooh, those are nice numbers. 36, 48, 60, 20. Nice how everything worked out. Of course, it was designed to work out. Okay, let's do question number 6. It says, Jonathan makes the conjecture. He says that if you multiply 2 matrices and then you inverse what you get, it's the same thing as if I inverse the first and I inverse the second. Show that his conjecture does not hold using the following matrices. Suppose A is -1, 2, 2, -3, and B is equal to 4, 1, 3, 1. So we want to show this is not hold. How do we do that? Well, we first calculate the left, AB, and I'm too tired to do it by hand, so edit 2 by 2, -1, 2, 2, -3. Edit second one 2 by 2, 4, 1, 3, 1. 4, 1, 3. Oops, 3, 1. And then we do A times B. So AB is 2, 1, -1, -1. And its inverse is 1, 1, -1, -2. Meanwhile, A inverse, B inverse, if I take matrix A and I inverse it, and I take matrix B and I inverse it, and I do that. Can I do this at once? Let's take a look. A inverse parentheses times B inverse parentheses. Yep, I can. And it gives me -3, 5, -1, 2. So we see, what do we see? That AB inverse does not equal to A inverse B inverse. Jonathan, you are an idiot. You are wrong. Not an idiot, just uneducated. B. Michelle claims, on the other hand, that AB, so this was a question mark and was ended up being wrong, that if you take AB inverse, you get B inverse A inverse. So if you inverse the products, you can multiply their inverses, but you got to switch the order. So part A, it says, first, verify Michelle's claim is correct. Use the B inverse A inverse above. So B inverse and parentheses times A inverse. And we see that B inverse A inverse equals 1, 1, -1, -2. And we have success. It worked. Just because it worked for this case doesn't necessarily mean it works for every case. Maybe the authors of the book picked a case to work. How do I know it really, really works? So it says for part B, choosing your own 2x2 matrices for A and B. Show that AB inverse equals B inverse A inverse. So this is your choice. There's infinitely many examples that you can do. So I'm gonna leave this to you. But number 3, part 3 says, prove that AB inverse equals B inverse A inverse. Prove that AB inverse equals B inverse A inverse. And it's actually not hard to prove. Proof. Here's the proof. What is the inverse of AB? The inverse of AB has the property that if you multiply it by AB, you get the identity. That is what that is what inverses do. They give you the identity. Well, if you do AB times B inverse A inverse, you also get the identity. And since multiplicative inverses are unique, therefore, AB, of course, we only did it on one side. Technically, it should be done for both, but let's not worry about it. Therefore, well, let's do it for both, just for completeness sake. If I do B inverse AB, as you can see, same idea holds. So you see that it works both ways, and therefore the inverse of a product is the reverse product of their inverses. Very important property from a theoretical perspective and for applications. Okay, 2 to go. Question number 7. Using the conversion table on page 386, that's my 3rd mistake in this section alone. It's on page 388. For a little bonus, you can look for the others. Decrypt the famous quote by James Joseph Sylvester. What is the famous quote by James Joseph Sylvester? Oh, never mind. They gave it to us. So we have our coding matrix. C is 1, 2, 3, 1, 1, 2, 0, 1, 2. And here is the encrypted message. 2, 2, 4. I'm going to go down. 2, 2, 4, 1, 4, 4, 83, 288, 202, 163, 84, 50, 49, 192, 109, 89, 279, 182, 174, 75, 49, 44, 38, 28, 15, 158, 80, 79. Let's move this over and make it smaller because this thing is still going on. 103, 71, 51, 96, 60, 51, 83, 50, 47, 220, 150, 131. Jeez Louise. Okay, so calculator time. First, second matrix, edit. First one, 3 by 3. 1, 2, 3. 1, 1, 2, 0, 1, 2. Whew, okay, second matrix, edit. This is a 3 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My calculator can handle it. 224. Now, of course, we go left to right. 288, 84, 192. Oops, 192, 279, 75, 38, 158, 103, 96, 83, 220. Did I put that in right? Yeah, okay, 220. 144, 202, 50, 109, 182, 49, 28, 80, 71, 60, 50, 150, 83, 163, 49, 89, 174, 44, 15, 79, 51, 51. Whoops. 51. Another 51. 47. 51, 51. Okay, and 131. Whew, okay. Second matrix. Well, first let's quit out this second matrix. So A inverse times B. Okay, so C inverse E equals 61, 77, 3, 39, 9, 77, 1, 19, 15. I am really interested in what this message is. 8, 20, 77, 5, 8, 18, 13, 5, 5, 1, 77, 1, 20, 13, 19, 9, 21, 15, 3, 19, 14, and 19, 9, 61. Okay, let's see what it is. Okay, 61 is quotation marks. 77 is a space. 3 is C. 39 is capital. This can't be right. Well, let's keep going, but this doesn't seem right. But let's keep going. 9 is I. 77 is space. 1 A. 9. This can't be right. This makes no sense. Something went wrong. Let's check my math. A. Whoops. A. 1, 2, 3, 1, 1, 2, 0, 1, 2. That looks good. Edit. B. Make sure I copied it correctly. 224, okay. 288, 221, 84, 50, 49, 192, 109, 89, 279, 182, 174, 75, 49, 44, 38, 28, 15, 158, 89, 103, 71, 51, 96, 60, 51, 83, 54. All right, put it in correctly. This makes no sense, unless it's a really weird quote. So let's try this again. So matrix A inverse. And we want to multiply that by matrix B. Let's try it across instead. So 61 is, again, quotation marks. 39, capital M, 1, A, 20, T, 8, H. Okay, this makes more sense. 5, E, 13 is M, 1, A, 20, T, 9 is I, 3, C, 19, S, mathematics, 77, space, 9, I, 19, S, space, mathematics is 20, T, 8, H, 5, E, space, mathematics is the 13, M, 21, U, 19, S, 9, I, C, 3, music, space, mathematics is a music. 15 O 6 F space. Mathematics is the music of 18 R 5 E 1A 19 S 15 O 14 N 61 quotation marks. Mathematics is the music of reason. Okay, so this does show one thing, that with this code, which is different than earlier, but this code, it was written side by side as opposed to in columns. Doesn't really make a difference which way you do it, as long as you know which way you're doing it. And then finally, question 8 says, develop your own cipher using matrices to encrypt a sensitive piece of information. Design your own conversion table and encryption matrix by assigning different numbers to each of the characters and numbers. Check your work by having a friend decrypt your message by giving them your encrypted message, encryption key, and conversion table. Many ways that you can do this, so I will leave it to you. And this takes us to the end of section 9.3. And we will soon move on to section 9.4, which gives more geometric applications for matrices. Hopefully this made sense. Feel free to ask any questions in the comments, and I will see you in section 9.4. Bye.